I hope everyone is doing well and doing fine after the break. I'm super excited to be back on the stage again. It's been 2 years that I literally stood on the stage. So I'm a little bit nervous, but also excited to talk to you about Kubernetes internals, etcd. So quick question, who knows about etcd, has heard about it, or played with it? Just quickly raise hands. Okay, that's good. It's a good start. Perfect. So because we do care about your safety, this is a 100% COVID-free presentation, obviously. And from an agenda perspective, we'll briefly talk about Kubernetes architecture, because I'm not going to assume everyone has heard about Kubernetes in depth before in etcd as well. And then we spend time on the etcd data model, because there's a lot of stuff going on behind the scenes in etcd that Kubernetes is heavily using. And then we'll bring together these worlds between Kubernetes controllers and operators and etcd. So even though I'll talk a lot about controllers and operators here as well, this talk is not just purely for Kubernetes platform engineers or software engineers. I hope that everyone either operating Kubernetes or building applications on top of Kubernetes can take something out of this presentation, because there's a couple of patterns that Kubernetes uses which are applicable beyond just Kubernetes and etcd. All right, let's start with a quick architecture. So when I talk about Kubernetes, I usually divide Kubernetes in 3 layers. One is the control plane, where we have things like the API server, the scheduler, controller manager, and obviously etcd, where data is persisted. Then we have the worker nodes, where we have the kubelet, which runs the workload, which are called pods in Kubernetes as the atomic unit. And then we have access layers, things how you interact with Kubernetes, like the REST API, SDKs, the UI, and kubectl. Behind the scenes, all these tools or SDKs use the REST API. So Kubernetes is a REST API, basically, if you will. And if you want to further simplify the architecture, it is literally the API server, everything talking through the API server in this control loop fashion. So all the objects that you've seen before are nothing but control loops, things that run in a tight loop, comparing the desired state that you or someone expressed with the current state of the system. So let's drill deeper a little bit into the API server. So let's assume we have a replica set we want to create. And the replica set says, I want run replica to be running. And so this basically means one pod of a specific application. So when we do kubectl create or in a controller or operator, behind the scenes, there's an HTTP post request against the K8s API server. And this can be considered a command, something that you intend the API server to do or accept. And there's a lot of things that go on in the API server, like validation and stuff, but eventually the object will be persisted in etcd. And then there's something called a watch, which is a stream of events, of changes inside Kubernetes that you or a controller or operator can register for notifications. And so these controllers run in their loop and basically react to these event changes through the watch. And watch is nothing but an HTTP GET request against the API server, and we'll see that a little bit at the end of the presentation, how this works under the covers. And then as part of the reconciliation, obviously something needs to be performed, like create a pod. So this controller here, the replica set controller, would send a command against the API server to create a pod, and then that would trigger another event, which the scheduler will pick up and will schedule the pod, which then will trigger another event, which the kubelet will pick up, and so on. So this is this kind of choreography that Kubernetes is performing. There's no central orchestrator that tells all the different actors what to do. It's rather this choreography between different controllers. And much has been written about this logic of control loops and reconciliation and choreography. And there's a couple of also good presentations by Tim Hawkin at the top here, talking more about different semantics like edge and level triggered semantics, all this wording which is thrown at you when you dig deeper into the Kubernetes machinery. But it's also natural that people have questions, especially when there's so many terms thrown around, not necessarily coming from a software engineering background, but maybe from control theory, which Kubernetes uses a lot internally for its architecture. And so I picked some random quotes here from the web from very knowledgeable and smart people who are either confused or are not happy with all these terminologies. And if you're like me, when you start with Kubernetes or dig deeper, there's actually more questions than answers usually, because there's so many different blog posts written or terminology thrown at you. So I decided to write a blog post to answer some of these questions which are scattered through the web, either on blog posts or different Kubernetes documentation or tweets. And so this led me down towards a very deep rabbit hole that I onboarded. So I got some questions here. What actually makes an event in Kubernetes? We talk a lot about events and event-driven systems, but then if you do a kubectl get events, for example, that is something very different than what we mean when we talk about events in these controllers and operators in Kubernetes. The next question is, well, if they are so important, how do controllers retrieve these events so they can react to them? And this gets us into reconciliation. And then the next question is, do we react on each individual event that we get, which is usually called edge-triggered semantics, or are we only reacting to a certain state that we see? So we are actually allowed to drop events on the floor because we are only asserting on the state, which is called level-triggered semantics. And then there are things like lister watcher and so on. So if you're familiar with kubebuilder, controller runtime, operator SDK, you will see some code paths which mention a lister watcher, for example, or reflector, or informer, or shared index informer, and so on. Can a controller miss events? Maybe, maybe not. If that's a problem, we'll see. The next question is, if we have multiple actors or controllers operating on the same object, say you have a deployment controller and an HPA and autoscaler, which write to the same object, could there be issues with these controllers having different views of the world when they have stale views based on older events and newer events? And how do we defend against and guard us against that? Why do Kubernetes resource lists, like pod lists, if you do a kubectl get pods or deployments, why do lists also have a resource version? So if you look at the metadata of returned lists and objects, you will find this thing called a resource version. Why can lists have a resource version? Because lists are very abstract. They are not kind of types or resources in there. And the next question is, if the resource version is so critical for all the stuff that we're going to discuss, why is it not persisted in etcd? So if you go deep in etcd and you retrieve basically what is stored inside, you won't find anything that has a resource version. It's not stored and persisted there. And last question, obviously, is the role that etcd plays in this Kubernetes architecture. Is it important? Is it not important? Why has been etcd picked? And so on. So I wrote this blog post on what's to the core in etcd, and was well received. It's a pretty long blog post, and we can't cover everything here in this presentation because the blog post alone is longer than this presentation. And so I urge you to read the blog post because it has more information around the internals and semantics of how etcd performs some of the stuff. Now, if you haven't heard about etcd, etcd is a distributed key value store for most critical data of distributed system. Key value store basically means you have keys and values and we write it in there and you can retrieve that. But remember that between etcd v2 and v3, which is the latest version, we don't really have a hierarchy anymore. Literally, it's a flat key value space. Whatever you put in there is literally just strings. So that has changed in etcd since version 2. But there's this nice thing called a watch, which we'll also show in a bit, which is basically you can tell etcd to not only like store data or return data, you can say, hey, inform me about changes inside your database that have happened. For example, if I write something in the database, give me these kind of notification changes so I don't have to ask all the time, hey, has something changed, right? Instead of polling, this is a push-based notification. So let's dig a little bit deeper into etcd before we cover the Kubernetes semantics. So I have prepared a Kubernetes environment, but here this is just a plain, what you see, and I'll explain in a bit, it's just a plain etcd Docker container. So there's no Kubernetes involved at this point in time. It's literally a plain empty etcd container. And it's not a cluster, it's just single node for the purpose of what I'm going to describe. And what we have here is we can interact with etcd on the command line using the etcd command line tool, etcd-ctl. And I just have aliased this to E here, basically that's the short handle. And then we say, etcd, give me everything that has a slash. Dash prefix means everything that starts with a slash, meaning if you know grep, the grep tools in Linux, it basically means everything that starts with a slash should be included in the response. And give me JSON output, formatted output, and pipe it into JQ, which JQ is just a nicely way of formatting all the stuff. So why am I showing and explaining that to you? Well, for two reasons. First of all, this is an empty cluster, meaning there's no key values returned here. So otherwise, there would be a key value array here. So this is currently an empty cluster. But the most important thing that I want to talk to you about is this revision thing. And if you don't take anything out of this presentation, remember this thing, the revision. The revision is like an auto-increasing counter, an integer, which is bumped up every time you modify something in etcd. So every write, every delete, those are typically the kind of operations that you perform in etcd, they will bump up this number. Whether you're just changing a field or a completely big object, everything bumps up this number. This is really important. So let's do something with this. Let's create some data in etcd. And I hope the terminal is readable. Like, is it readable in the back? Or okay, cool, thanks, perfect. So I just created 5 keys in etcd, like keys slash and then 1, 2, 3, 4, 5. Let's retrieve the keys. And because keys and values in etcd, when you interact with it, are base 64 encoded, I also have to do some JQ magic here to decode them on the fly. But what we now get back in the header is always returned. Header is like metadata that you interact with etcd. The header returns as a revision, which is 6. Makes sense because we started at 1. Every cluster or member starts at 1, and we create 5 keys, so 1 plus 5 is 6. So 6 modifications in the store. And then we get back our key value pairs, KVS. And we see here key 1, key 2, and then we see a value. What we also have is a create revision, a mod revision, and a version. Every key in etcd has these 3 properties. Create revision and mod revision tells us when this key was created, the revision, and when it was modified. If those numbers are the same, like 2 and 2 in this case, it means this key just has been created. And then the version also tells us how many times this thing has been changed. In this case, just once, because it was just created. And so this is the same for all the other keys, right? They just have different create revisions because, again, every change in etcd bumps us this number. So key 3 here is at number 4 because we started at 1. Okay, let's do another modification. Let's overwrite the value of key 1 and make it a value A1 or 1A. We see that the revision has been bumped up again, right? That's what we expect. And now let's take a look at the key just so you trust me as well. So those are this is the key here. I didn't base 64 decode it, and the value is A1 now. And we see create revision stays at 2, so we know that was when it was created, and mod revision is now at 7, and the version has been bumped up to 2, because 2 modifications, basically. Let's delete it. So I'm deleting this key. It's deleted, and you also see that the header being returned is at revision 8 now, because every delete also modifies the store, so we bump up the revision. So let me show you that it's actually deleted. So I'm getting all the keys, and you don't see key 1 here anymore, right? It's deleted. Let's now do time travel queries in etcd. So this is something very important because what etcd does behind the scenes is it doesn't really delete the key, it will only mark it as being deleted. And so every modification in the store is basically kept until you tell etcd to compact or defrag the key space. We haven't done this for now, so still the data is in etcd. So what I can do now, I can ask etcd, give me key 1 at revision 7. I picked revision 7 because I know it existed at this point in time, but you can also work backwards in time and find this key. So let's ask etcd, and we find that by saying, hey, etcd, give me everything up to this revision, this basically increasing log counter, if you will, with 1, 2, 3, 4, 5, 6, 7, 8, we basically go back in time now. This is time travel queries in etcd. And we now see that the current revision is at 8, so we always know, okay, we did a time travel query, right? Because we asked for 7, we are currently at 8, so we went backwards in time. And the key 1 here is at mod revision 7, that's when we modified it, and the value is A1, 1A. We can also go further back in time by saying revision 6 in this case. And then what we get back is the key, how it looked like when it was created, because between 2 and 7 there weren't any modifications. So that's how the key is basically represented at this point in time. So let me create this key again. So technically it's deleted, right? At the last one, what we did is it's deleted. So now I'm creating it again. Revision gets bumped up again. We are at revision 9 now. And now let me show you the actual underlying database, because so far we've only seen how etcd looks like from like the logical view, how you interact or an operator interacts with. But beyond etcd, there's a database. And the database is also a key value database using BoltDB. And BoltDB has a different representation that I'm also going to show you to you. So what I do is I copy the database to my local machine here, and then I'm going to use the tool etcd-dumpdb, which is a tool provided by etcd, by the community, where you can iterate over the physical database. And that's useful for like debugging, introspection, because you can literally take a look at the physical view of the database. So what we see here in the database is we see something called a ref and the value. So the database is a key value database as well. But the ref here, in this case, the key is a number, 2, 3, 4, 5, 6, 7, 8, 9. And what this number is, it's basically this revision counter which gets bumped up every time. And the value in the database is the key, the logical key, in this case key 1, 2, 3, 4, 5, and all the changes. Then also a value, and then created, modified, and version. So to simplify this, the key in the database, in the physical database, is the revision counter, not the key that you use. Like it's not key 1, key 2. It's literally that change, modification, this revision. And then the value is the more complex representation of key value pairs that you interact with in etcd. And so from a physical perspective, what we do is we have an append-only sequence of these changes. And etcd internally keeps track of this logical key that you create, key 1, key 2, key 3, whatever, and maps that to the physical representation under the hood. And only this way it's possible to have time travel queries, because etcd knows and stores these revision counters internally and then does a mapping between logical keys to physical revision numbers. And so we can do time travel queries. And so if you look here at revision 7, 8, and 9, where we did a modification, a deletion, and another creation of the key, we see that the value has changed. And when we deleted it, the actual value was completely erased and created, modified, and version is set to 0, meaning it's a tombstone marker, this key is being deleted. If I would go ahead and compact the etcd key space now, this key would be deleted, like physically deleted from the database. But for now, it's still there. And this is important because it allows us time travel queries. All right, let's do one more thing, which is watches. So I'm going to create a watch, which is almost like a get, but it basically is like a subscription for give me all the changes on this specific key 1 here, and print them out in a JSON format. So because right now I'm not doing any modifications, I need to modify something, otherwise we won't see anything. So I just modified here on the left, I modified the key again, and on the right we got a watch event. And the watch event also includes the header with the revision. So we also know from watches what the store currently is, what the time, if you will, is currently at the store. And then we get back events. So instead of key VS, we get back events. And then these events have key value pairs, whatever the key was that we modified, and then create revision, mod revision, and version. So basically, having these watches, we have efficient change notifications of how things get modified in etcd's state store under the covers. This is still nothing Kubernetes, right? This is still very low-level etcd state store. And now, to talk a little bit more about Kubernetes, if you have ever looked at a Kubernetes object, when you do Kubernetes like get pod or whatever, in this case, there is metadata associated with any object. And there's like a name, there's labels, there's a namespace, and so on. But there's also something called a resource version in Kubernetes. Every object has a resource version. And this resource version is important because it tells Kubernetes and you or a controller what the representation, what the store at this point in time was. So not just for this object, but basically based on this number, you know that this object was represented at whatever 24,000 something at that point in time in etcd. So we'll talk more about how these numbers work together, but a revision in etcd is projected as a resource version in Kubernetes for some very important concepts. So let's go back to the slides to explain a little bit more about revisions and resource versions and why they are important. So if you ever have written a Kubernetes controller or operator, there's something called a reconciler. A couple of years before, it was very much low-level logic that you would have to write in Kubernetes to build a controller and operator, as Robert yesterday spoke about building operators. But these days, it's rather easy to build a controller or operator on Kubernetes using this interface, the reconciler interface. And the reconciler interface is nothing but you have to write your business logic inside this function here. Where's my mouse? Okay, here we go. Inside this function. And this function gets passed a request. And the request is a name and the namespace of an object to be of your interest. Say you write a pod operator, well, that will be a pod and the namespace. Now, two things are important here. One is that reconcile is supposed to reflect the actual state that you see, that your controller sees, with the desired state. Say, I want 3 pods, and currently there's just 2. So your work is to go from 2 to 3 pods, right? That's the desired state logic that you're supposed to implement. And then also it says that reconciliation is level-based, meaning that actions aren't driven off changes of individual events, but the state that you see. And this is a fancy way of saying, instead of reacting to each individual change or watch event, you're literally just looking at something that comes in and has a state representation, like a spec, for example. Spec replicas is a state representation. And to make an analogy here, consider an example where you would have to write logic to do a addition, like 1 plus 1 plus 1, and then give a sum at the end of the day. If you miss one of these events, your result might be different, right? Instead of having 3, the result might be 2, or depending on the number of events you miss. In level triggered state, you wouldn't write this logic. You would say the sum is 3. And if I give you, like, the sum is 3, 3, 3, you get 3 events, and you miss one of this, it doesn't really matter, because the state that you get 3 is the number that is currently present and what you're supposed to do. And that's the difference between edge and level triggered semantics, where Kubernetes uses level triggered semantics for resiliency purposes, so that you can actually lose events under the covers. And then it's unfortunately not that simple. Like, there's a lot of stuff going on under the wires, and you're not supposed to read this stuff. I'm just trying to show what's going on here. So on the left here, we have all the stuff that is inside a Kubernetes controller. And here on the link, you can zoom in and have all the details. In the middle, there's the API server, and on the right, there's the etcd. And there's a lot of steps involved behind the scenes to make this magic happen and work, which usually you don't have to worry about when you write these controllers. But if things go wrong, or if you have questions, or you're just curious, then you will start naturally asking questions and digging deeper into the system. And so there's one important thing in a controller, which every controller under the covers also uses, and that's called the lister watcher. Because we haven't answered the question of how these events, these changes, come into your operator, right? At some point in time, you actually need to subscribe to events. And the way this is done is through a lister watcher. And a lister watcher in Kubernetes is something that knows how to list something and to watch something. Similar to what we already did with etcd. Etcd get was a list, and etcd watch was the watch. So I already did that behind the scenes without actually talking about the lister watcher here. Why is the lister watcher important? And this is where it gets a little bit like deeper into machinery, but it's very important for the resiliency of Kubernetes and all the controllers involved there. So I hope you can read it in the back, otherwise I'm going to explain what's going on here. So in blue, we have a controller, or kubectl. So this example is done using kubectl, so you can do it literally on your own machine without writing a controller, because the logic is the same whether you're using kubectl or building an operator. So what kubectl does in any operator is, first, in the list phase, it tries to retrieve all the objects that it cares about. In this case, it's objects of pods in the namespace default. Let's assume we are building an operator which only cares about pods in the default namespace. So it issues an HTTP GET request against the API server, and then the API server here in green will pick up that resource, like v1 namespace default pods, and transform it into an etcd registry path. So Kubernetes internally projects these HTTP resource paths into registry paths in etcd. And then the registry path is organized as registry/type pods/namespace, here in this case default. And then we say with prefix, which means everything that matches this string, which includes then the pods, because the pods have this starting string, right? It's like a grep. And then etcd responds with the header. We've seen that before. The header has a revision. We know that the revision is the point in time the store is, the clock of the store, if you will. And then it has these key value pairs, which I omitted for like the sake of brevity here. And then the API server takes this etcd response, which is, by the way, in a gRPC call. It takes the API, the etcd response, and projects this into an HTTP response, because in Kubernetes everything is HTTP based. And it uses this resource version and puts it as a pod list response. So that's when you trace the requests under the wires, you will actually see this data coming out of Kubernetes. And so you get back a pod list, a list of pods in namespace default, and the list has a resource version. So now we already answered the question why lists can have resource version. This is nothing but telling you that when you did the query, that was the point in time etcd was at. So basically like the snapshot. So you know that your query was at time 3788. Now this is important, because after the list, when you get all the stuff and you basically have it in your cache or in your local system, now you want to subscribe to a watch. If you wouldn't have a number like 3788, you wouldn't know when to start watching. So there could have already been changes, right, in between. So this number, this revision or resource version, serves as a stable cursor in this append-only log, where you're guaranteed to not miss an event in this case. With a little asterisk, there could be an issue with that. We'll cover that in a bit. So here what the client now does, the second phase is it does another HTTP GET, and same like namespace default pod, and then appends two parameters. One is the resource version, the number that it got from the previous pod list call, and watch equals true, which indicates the API server now it needs to stream these changes back to controller or kubectl here. So it now performs a watch, API server now performs a watch against etcd, and it passes this revision to etcd, 3788 plus 1, because it's the next, I want the next one, right? And so etcd now starts feeding back these events if there are changes. For example, here we get back an event that has a mod revision of a pod, in this case of 4067. Remember that in between these changes, there could be other changes: endpoints, services, leases, stateful sets, replica sets. A lot of things that bump up this number, right? So it's not like we get 3789 for the pod here, because there are a lot of changes happening in between. And then this response is used by the etcd, by the API server, and we get back an event of type modified for the object kind pod of name something something pod, and the resource version. So the resource version that we saw earlier in the kubectl snippet is now projected in here, which we got back from etcd. And this is important. I'll cover that in a bit. So let's dig deeper a little bit, and it's hard to read, so I'm going to explain what's going on here. So this is a very simplified view of the physical view now of the database in etcd, not from an API server perspective. So we have a controller, or kubectl, if you will, in blue, and we have the physical database representation to make this a little bit more clear. And so we have 7 current changes in the data store. The data store basically had 7 write operations. And there's a pod which was created, there's some other stuff, replica sets, whatever. And then we deleted this pod, there's another pod, and so on. And so coming back to this list case that we saw earlier, what happens here, the controller does a list again. It retrieves back these pods. In this case, there's just one pod in here because pod 1 has been deleted, so we only get back pod 2. The revision is at 7 because that is the change of the underlying build database. And then let's assume there are 3 more changes since we did the list, 8, 9, and 10, right? Because this is this integer which always gets incremented. And let's assume we have pod being created, pod being updated, and then something else is deleted. Now, because the controller does a watch, what it will get back is basically an added event for pod 1 at 8, and a modified event for pod 1 at 9. And so this is what your controller operator logic will basically get fed as an event internally and then do the reconciliation, right? And so this is the whole machinery under the covers of Kubernetes, where we use etcd events, changes, watches, and revisions, and then project them into Kubernetes API server resources like pod lists or pods being returned, so that your controllers can be stateless. So they come up, they have no state, they make a get, you get all the pods in there, and then you start subscribing to these changes, right? And so you get every change on objects like pods, for example. And when you crash, you come back up, you do a get, and then you do changes. So that means your operator logic can be free from state, which is nice because you're basically writing stateless logic in your operator, and you defer the whole complexity to Kubernetes. But there's other advantages of this resource version and revision, which I'm going to cover at the end now. So just to summarize a little bit, what is an event in Kubernetes? Unfortunately, event is an overloaded term in Kubernetes. One kind of type of events is audit events in Kubernetes. And this is not the type of event I was talking about. I was talking about change events that controllers use under the covers to reliably detect changes to Kubernetes and then react and do this whole reconciliation. Before that, so if you wouldn't have these change notifications, all the controllers would literally constantly ask the API server, do you have new stuff? Do you have new stuff? And you can imagine that this doesn't really scale, right? At nodes of like 5,000 or 10,000 nodes, that doesn't scale. So events, change notifications are very important. Now, the way that's implemented, and this is a very important pattern which you can also use beyond Kubernetes, and even if you're not like an etcd expert or you never want to be one, the list or watcher pattern is pretty, for me, impressive, because it has this list phase where it says, give me everything that you have at this point in time, like an offset, and then let me start watching from here. So because having this stable cursor, this revision or resource version, we know that we are guaranteed to not miss anything because it's the sequence of events. It's almost like the clock, right? And you say, give me everything after 1:15, for example. Next question, can a controller miss events? Yes, it can. Maybe there's a crash and you are down for 5 minutes and there have been changes in the system and you come back up. You could miss delete events because the things are gone. The list would not return your delete events because those objects are deleted. Is that a problem? Well, it depends on your logic. If you need to perform cleanup logic, for example, you're configuring ELBs or you're spinning up virtual machines like in a different control plane, well, that is a problem because you're not deleting other stuff, other resources that have been deleted. So there's a concept in Kubernetes called a finalizer, where for every object that you create or own, you can put yourself in a list. It's just a string list. And you say, hey, if something happens to this object and it gets deleted, I'm going to be I have to be notified about that. And so if your controller crashes, but you have been part of this list, Kubernetes is just holding that object. It's not deleting that object. So when you come back up, you will still see that object, but marked for deletion. And then you do your work. If you crash again, well, doesn't problem because you come back up and you do your work until you say, oh, I'm done, and I'm removing myself from the list of finalizers. And if an object doesn't have any finalizers left, then it's safe to delete that object. And so it's fine to miss events because we have finalizers and other objects like mark for deletion in Kubernetes that prevent us from missing critical events for cleanup. How do we deal with eventual consistency in multiple actors? Let's say we have the pod autoscaler and the deployment controller and they work on a deployment. How do we make sure that they are not stepping onto their own toes when they are configuring or modifying the same object? Well, this is again where resource version comes into play. Because we know that resource version is backed by the store revision in etcd, we can use it to perform a compare and set operation and say, hey, here's my representation, resource version 5. And if that resource version is older than the current version of that object, Kubernetes is going to reject us, and we have to read that object state again. So we basically fence off old clients or stale clients here. Next question, why do Kubernetes resource lists have a resource version? Well, we already know that. It's again projected from the version, from the store revision, so that we can have this list and watch semantics for these controllers. So it's very important to have that. And last one, if the resource version is so critical, why is it not persisted in etcd? Well, if you have followed, obviously it was very fast here, but you might know we don't need to persist that resource version in etcd because it's already there as part of the revision. So what Kubernetes does is it's basically stripping that information before it writes to etcd, because that's redundant, it's already in etcd as part of the revision. So what Kubernetes does when it reads stuff, it reads the object, and then it projects the resource version into that object. So we not only save space, but we also avoid race conditions between, oh, did we actually write the same revision or the same resource version in a transaction manner? So you won't find anything resource version in BoltDB. If you look up the database, there's nothing inside for resource version, and it's not needed because we basically map resource version and revisions. Last thing is, which role does etcd play in the Kubernetes architecture? Well, it's not only a highly available distributed key value store, but it also gives us this multi-version concurrency control where we can traverse back in time into the etcd state store, replay information, have different clients work at their own pace in terms of these events, and then also have a strongly consistent key value store based on Raft consensus, which I didn't have time to cover today. So just to close this off, there's 2 talks that I gave which are more and longer and in-depth around this topic. So there's a 90-minute presentation on this topic, which has I'm walking slowly about this one. And then the other one is building an operator in Go, where I also cover semantics of things that you have to keep in mind when you build an operator to make them resilient and robust, and basically all the issues with missing events and all the stuff. So that is covered in this presentation. So before I close this off, at the end of the appendix, so I'll upload the slides, there's a lot of links that I have covered for research work that we've done around time travel issues and bugs that we discovered in Kubernetes controllers and operators, because it's not that easy to write robust and resilient operators. So this time travel query is good, but it also has corner and edge cases because of caching and other semantics. There's also links in the presentation about Kubernetes API conventions, which cover more of these kind of things, building operators and how the Kubernetes API server works. So if you're interested, look at the appendix in the slides there and there. With that, I think I'm still good on time and appreciate being here back on stage and having you as the audience. Thank you very much.